Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 94, AI Alignment as Translation Between Humans and Machines, published on the 8th of April 2020 by Rohans. Highlights. Link, Alignment as Translation by John S. Wentworth, summarized by Rohan. At the very high level, we can model powerful AI systems as moving closer and closer to omniscience. As we move in that direction, what becomes the new constraint on technology? This post argues that the constraint is good interfaces, that is, something that allows us to specify what the AI should do. As with most interfaces, the primary challenge is dealing with the discrepancy between the user's abstractions, how humans think about the world, and the AI system's abstractions, which could be very alien to us. For example, perhaps the AI system uses detailed low-level simulations. The author believes that this is the central problem of AI alignment, how to translate between these abstractions in a way that accurately preserves meaning. The post goes through a few ways that we could attempt to do this translation, but all of them seem to only reduce the amount of translation that's necessary. None of them solve the chicken and egg problem of how you do the very first translation between the abstractions. Rohans Opinion. I like this view on alignment, but I don't know if I would call it the central problem of alignment. It sure seems important that the AI is optimizing something. This is what prevents solutions like make sure the AI has an undo button or off switch, which would be my preferred line of attack if the main source of AI risk were bad translations between abstractions. There's a longer discussion of this point here. There's a link to a comment on the alignment forum. Section Technical AI Alignment. Subsection Agent Foundations. Link Two Alternatives to Logical Counterfactuals by Jessica Taylor. Subsection Learning Human Intent. Link State-Only Imitation with Transition Dynamics Mismatch by Tanmay Gangwani et al., summarized by Zach. Most existing imitation learning algorithms rely on the availability of expert demonstrations that come from the same MDP as the one the imitator will be evaluated in. With the advent of adversarial inverse reinforcement learning, AIRL, discussed in Newsletter 17, it's become possible to learn general behaviors. However, algorithms such as Gale, also from Newsletter 17, are capable of learning with just state information, something that AIRL was not designed for. In this paper, the authors introduce indirect imitation learning, I2L, to try to merge the benefits of both Gale and AIRL. The basic sketch of the algorithm is to first use a generalization of AIRL to imitate demonstrations via a buffer distribution, and then focus on moving that buffer closer to the expert's demonstration distribution using a Wasserstein critic, a smoother way to train GAN networks. By combining these two approaches, agents trained with A2L learn how to control ANT in regular gravity and can generalize to perform in simulations with differing parameters for gravity. For the suite of GIM continuous domains, they show consistent advantages for I2L over other algorithms such as Gale, BCO, and AIRL when parameters such as friction, density, and gravity are changed. As a prerequisite, there's a link to the Wasserstein GAN, and if you want to read more, you can read the paper Learning Robust Rewards with Adversarial Inverse Reinforcement Learning. Zach's opinion. The main contribution in this paper seems to be deriving a new bound so that AIRL can handle state-only imitation learning. The use of indirection via a buffer is also interesting and seems to be a good idea to provide stability in training. However, they did not do an ablation. Overall, it's aesthetically interesting that this paper is borrowing tricks such as buffering and Wasserstein critic. Finally, the results seem promising, particularly for the sim-to-real problem. It would be interesting to see a follow-up to gauge whether or not I2L can help bridge this gap. Link The MineRL Competition on Sample-Efficient Reinforcement Learning Using Human Priors, a Retrospective, by Stephanie Milani et al., summarized by Rohan. This paper reports on the results of the MineRL competition discussed in Newsletter 56, in which participants had to train agents to obtain a diamond using a limited amount of compute, environment interactions, and human demonstrations. While no team achieved this task, one team did make it to the penultimate milestone, obtaining an iron pickaxe. The top 9 teams all used some form of action reduction. That is, they constrained their agents to only take a subset of all available actions, shaping the space in which the agent had to learn and explore. The top 4 teams all used some form of hierarchy in order to learn longer options that could then be selected from. The second place team used pure imitation learning, and so required no environment interactions, while the 8th and 9th place teams used pure reinforcement learning, and so required no human demonstrations. Rohans Opinion. I was surprised to see pure RL solutions rank in the leaderboard, given the limitations on compute and environment interactions. Notably though, while the second place team, pure imitation, got 42.41 points, the 8th place team, pure reinforcement learning, only got 8.25 points. More generally, I was excited to see an actual benchmark for techniques using human demonstrations. So far, there hasn't been a good evaluation of such techniques. It does seem like Minecraft benefits a lot from hierarchy and action pruning, which we may not care about when evaluating algorithms. Section Sample-Efficient Reinforcement Learning Through Learning from Demonstrations in Minecraft by Christian Schaller et al., summarized by Rohan. This paper explains the technique used by the 3rd place team in the MineRL competition discussed above. They used behavior cloning to train their neural net on human demonstrations, and then used reinforcement learning, specifically Impala, with experience replay and advantage clipping to improve. There are more details about their architecture and design choices in the paper. Subsection Handling Groups of Agents. Link Equilibrium and Prior Selection Problems in Multipolar Deployment by Jesse Clifton, summarized by Rohan. Consider the scenario in which 2 principals with different terminal goals will separately develop and deploy learning agents that will then act on their behalf. Let's call this a learning game, in which the players are the principals and the actions are the agents developed. One strategy for this game is for the principals to first agree on a fair joint welfare function, so that they and their agents are then licensed to punish the other agent if they take actions that deviate from this welfare function. Ideally, this would lead to the agents jointly optimizing the welfare function, while being on the lookout for defection. There still remain 2 coordination problems. First, there's an equilibrium selection problem. If the 2 deployed learning agents are Nash strategies from different equilibria, payoffs can be arbitrarily bad. Second, there's a prior selection problem. Given that there are many reasonable priors that the learning agents could have, if they end up with different priors from each other, outcomes can again be quite bad, especially in the context of threats, as discussed in Newsletter 86. Rohans Opinion. These are indeed pretty hard problems in any non-competitive game. While this post takes the framing of considering optimal principals and/or agents, and so considers Bayesian strategies in which only the prior and choice of equilibrium are free variables, I prefer the framing taken in our paper discussed in Newsletter 70. The issue is primarily that the optimal thing for you to do depends strongly on who your partner is, but you may not have a good understanding of who your partner is, and if you're wrong, you can do arbitrarily poorly. Subsection Forecasting. Link Openness Norms in AGI Development by Sublation, summarized by Rohan. This post summarizes 2 papers that provide models of why scientific research tends to be so open, and then applies it to the development of powerful AI systems. The first models science as a series of discoveries, in which the first academic group to reach a discovery gets all the credit for it. It shows that for a few different models of info-sharing helps everyone reach the discovery sooner, but doesn't change the probabilities for who makes the discovery first, called race-clinching probabilities. As a result, sharing all information is a better strategy than sharing none, and is easier to coordinate on than the possibly better strategy of sharing just some information. However, this theorem doesn't apply when info sharing compresses the discovery probabilities unequally across actors. In this case, the race-clinching probabilities do change, and the group whose probability would go down is instead incentivized to keep information secret, which then causes everyone else to keep their information secret. This could be good news. It suggests that actors are incentivized to share safety research, which probably doesn't affect race-clinching probabilities, while keeping capabilities research secret, thereby leading to longer timelines. The second paper assumes that scientists are competing to complete a K-stage project, and whenever they publish, they get credit for all the stages they completed that were not yet published by anyone else. It also assumes that earlier stages have a higher credit-to-difficulty ratio, where difficulty can be different across scientists. It finds that under this setting, scientists are incentivized to publish whenever possible. For AI development, this seems not to be too relevant. We should expect that with powerful AI systems, most of the profit, comes from the last few stages, where it's possible to deploy the AI system to earn money. Rohans Opinion. I enjoyed this post a lot. The question of openness in AI research is an important one that depends both on the scientific community and industry practice. The scientific community is extremely open, and the second paper especially seems to capture well the reason why. In contrast, industry is often more secret, plausibly due to patents, which we discussed in Newsletter 88. To the extent that we'd like to change one community in the direction of the other, a good first step is to understand their incentives, so that we can try to then change those incentives. Subsection Miscellaneous. Link Takeaways from Safety by Default Interviews by Asya Burgal, summarized by Rohan. This post lists 3 key takeaways from AI impacts conversations with optimistic researchers, summarized mainly in Newsletter 80 with one in Newsletter 63. I'll just name the takeaways here, see the post for more details. 1. Relative optimism in AI often comes from the belief that AGI will be developed gradually and problems will be fixed as they're found rather than neglected. 2. Many of the arguments I heard around relative optimism weren't based on inside view technical arguments. 3. There are lots of calls for individuals with views around AI risk to engage with each other and understand the reasoning behind fundamental disagreements. Rohans Opinion. As one of the people interviewed, these seem like the right high-level takeaways to me. Section Other Progress in AI. Subsection Reinforcement Learning. Link Robots Learning to Move Like Animals by Bin Peng et al., summarized by Rohan. Previous work, discussed in Newsletter 28, has suggested that we can get good policies by estimating and imitating poses. This work takes this idea and tries to make it work with sim-to-real transfer. Domain randomization would result in a policy that would be robust to all the possible values of the hidden parameters, such as friction. To make the problem easier, they do domain randomization, but give the agent access to a latent representation of the hidden parameters, so that its policy can depend on the hidden parameters. Then, to transfer to the real world, they simply need to search over the latent representation of the hidden parameters in order to find one where the policy actually works in the real world. In practice, they can adapt to the real world with just 8 minutes of real-world data. If you want to read more, you can read the paper, Learning Agile Robotic Locomotion Skills by Imitating Animals. Rohans Opinion. This is a cool improvement to domain randomization. It seems like it should be distinctly easier to learn a policy that's dependent on the hidden parameters, and that seems to come at the relatively low cost of needing just a little real-world data. This concludes Alignment Newsletter number 94. For more information, you can go to rohanshah.com/alignment-newsletter, where you can find all of the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.